All right, so for written this all out, I was in the last video. I was about to finish part 3a, but anyhow, so this was the equation that we had set up. 1.989 times 10 to the minus 25th joules times meters, divided by the energy that we had discovered of that particular photon, which was what was the photon? The photon was it had a wavelength of, here, let me look again. It was energy of 2 electron volts. Anyhow, so we just converted 2 electron volts to joules. You get 3.2 times 10 to the minus 19th. So the top number divided by the bottom number gives us 6.216 times 10 to the minus 7th meters. Now, if I move the decimal place 2 places to the right, then that becomes times 10. Because the decimal place has to return to that same spot to keep the same number. That becomes 621.6 times nanometers, times 10 to the minus 9th. And the reason that we do that is this is actually in the visible part of the spectrum, and that's in fact red light. Let's do the next problem, which is still question problem number 3, but part B. They said, okay, this time if the energy is 0.1 electron volts, so that's a very small amount of energy, let's convert that from electron volts to joules. So we use the same conversion. 1 electron volt, I didn't write a 1 right there. 1 electron volt is 1.6 times 10 to the minus 19th joules, and so that's equal to 1.6 times 10 to the minus 20th joules is the amount of energy for that. Instead of in electron volts, now it's in joules. And then we use this equation just like we did for part A. Lambda is equal to hc divided by the energy, and if the energy is in joules, we need to use this the 1.989 times 10 to the minus 25th joules times meters, and so our answer will come out in meters, right? Because the joules cancel, right? We're canceling the joules, and so you just do the the division here, and you get 1.24 times 10 to the minus 5th meters, and that is let's see, that is that in the I think that's in the microwave region. So that's a very tiny amount of energy. All right, let's finish this problem up. So in part C, they give us the energy of an X-ray is 5,000 electron volts, right? Remember the other ones we were talking about, just like 2 electron volts and 0.1 electron volts. The 2 gave us energy in the visible part of the spectrum, a photon in the visible part. This one gave us an energy in the I think it was in the microwave region. All right. So anyhow, we do the exact same thing. 5,000 electron volts. 1 electron volt is 1.6 times 10 to the minus 19th. That doesn't really look like a 9. Doesn't look like a 1. Times 10 to the minus 19th joules. The electron volts cancel, right? So we can cancel those, and you get you get 8 times 10 to the minus 16th joules. All right, and then we use our equation. So here's our equation. Remember, lambda is equal to the constant hc, and it's got to be in this form because we have our energy in joules. So we just calculated the energy of 5,000 electron volts into joules, and so this is this would be 8 times 10 to the 16th times 10 to the minus 16th joules, and then of course the joules cancel, and that will give us our energy our wavelength in meters, right, which is ultimately what we want. And so our answer is comes out to be a very tiny 0. Let's see. Here, actually, let me write it this way. Not 0. That's the next step. It comes out to be 2.5 times 10 to the minus 10th. 10 to the minus 10th meters. 10 to the minus 10th meter. Oops, that's the 10 to the minus 10th meters. And so if you actually move the decimal place one place to the left, it would be 0.25 times 10 to the minus 9th meters, which of course would mean that the wavelength of this would be 0.25 nanometers, right? And of course, you could have done that more directly. Obviously, I did it this way just to show you guys that you can do these. You can do different conversions. Okay, let me just show you this part C in the using the other the other constant for H times C, right? So instead of this one, we're going to use, all right, so lambda is going to equal, and it'll give you the same answer. You'll see 1240 electron volts times nanometers, right? And then you divide that by the energy, right? And so the energy in this particular case was 5,000. Again, you could have done this with part A, part B as well, all right? 5,000 electron volts. And so, see, this gives you, I mean, this is, we're going to ultimately get this answer, which we got by using this other constant, but it's always kind of reassuring to see that you get the same thing. All right, so let me get my calculator here. So let's see, 1240 divided by 5,000. It comes out to be, yeah, it's like 0.248, which of course would round to 0. Remember the answer, since the electron volts cancel, the answer is in nanometers, right? So it's going to be 0.248 nanometers, or 0.25, right? 2.25 nanometers, which you see that they're both the same, right? Either way that you do it, it works out exactly the same, which that's always a good thing. It's a good way to check yourself. In number 4, they want us to figure out the energy of a gamma ray. So that this symbol is the Greek letter for gamma. The energy of a gamma ray compared to the energy of a radio signal. And they kind of mix things up a little bit. They give us the fact that the radio signal is 10 megahertz. That's an M. I know it doesn't quite look like an M. And they also give us the wavelength. Instead of give us the frequency of the gamma ray, they give us the wavelength as 1 nanometer. So we got a little bit of work to do. So we could either change both of these into hertz, which is perfectly fine, or we could change them both into wavelength. All right. So here's what I mean by that. So what this is going to equal. So ultimately, what this is going to equal is, remember, for the energy of any photon is hc over the wavelength, right? And of course that's the wavelength of the gamma. That would be on top, divided by hc divided by the wavelength. I'll just use an R for radio. And so see, notice the HC's cancel, and so if you rearrange this, you notice it'll put the wavelength of the radio on top, right? So it's lambda radio, or R radio, divided by lambda of the gamma. Now we know the wavelength of the gamma, but they didn't give us the wavelength of the radio. But of course, 10 megahertz. We also know the fact that is equal to the speed of the let's rearrange it this way. We know that the wavelength lambda for in general is equal to the speed of light divided by the frequency. All right, so if we change so we're going to actually calculate lambda radio right now, or rad, as I put up here. Rad, I guess I should try to write that in there. So lambda radio is going to be 3 times 10 to the 8th meters per second divided by the frequency they gave us. Now they told us it was 10 megahertz, but we need it to be in hertz, right? This meters per second, and so it's going to be 10 mega is times 10 to the 6th hertz, right? And so hertz and 1 over seconds cancel, and so that gives us, what does that give us? Let me see. The gamma ray is it 30? Yeah, 30. So it comes out to be 30 meters. No, the radio, sorry, not the gamma. The radio comes out to be 30 meters. All right, so now that we know that, we can calculate this up here, right? So this is just 30 meters divided by the wavelength of the gamma, which they give us down here in nanometers, so we need that to be in meters. Of course, that's easy because you remember your metric prefixes, and nano is just times 10 to the minus 9th meters, of course. And so the meters cancel, and so that gives us, here, let me pause this for a second. So the energy of the gamma, just to remind of where we're at, we had left off with 30 meters divided by 1 times 10 to the minus 9th meters, and so that's the energy of the gamma, the gamma photon divided by the energy of the radio photon. So 30 divided by 1 times 10 to the minus 9th turns out to be 3 times 10 to the 10th, and so now we can actually answer the problem, which was really how much more energetic is a gamma ray photon than a radio photon. All right, so the gamma ray, all I'm doing is just multiplying both sides by the energy of the radio. So I'm just going to bring that right here. All right, so the energy of the gamma ray is 3 times 10 to the 10th, right? That's an enormous number, times the energy of a radio. Of, that particular radio photon. So, I mean, it's an enormous difference in energy. All right, let's move on to what's the next one? Number 5. So number 5 is really, you just look these up, okay? So they're asking us what the alpha line is. This is in the Balmer series, by the way, just to let you know. It doesn't. Anyhow, the H alpha series, the H beta series, and the H gamma series. And so the H alpha series is, a transition in the from n equals 3 to n equals 2. The quantum level n equals 3 to n equals 2, and so you would have a photon of 656.3 nanometers. By the way, when you look at the spectrum of the emission spectrum of hydrogen, this is the red line that you see. So this is the red line. This next one, the beta emission is or absorption, right? If you have continuous spectrum passing through cooler gas. This one is kind of aqua or green, and then the last one is blue. So that's the blue end of the spectrum, right? Because the spectrum goes from red to blue. Longer wavelength is red, shorter blue. All right, and Yeah, so these are, again, this is part of the Balmer series.